The faint smudge in the autumn sky between Cassiopeia and Pegasus is the single most distant thing your naked eye will ever resolve, and the light reaching you tonight from it left its galaxy more than 2 million years before your species existed. It is called Andromeda. It is the closest major galaxy to our own, and it is, by every measure physics can describe, permanently out of human reach. Tonight we are going to walk through the cascade of reasons why distance, energy, biology, the speed of light, the strange geometry of space-time, and the slow approach that arrives long after the sun has died. So get comfortable, settle in. There is no urgency to this impossibility, and quite a lot of strangeness to unfold. Part 1. The bright smudge that has always been just out of reach. Step outside on a clear autumn night, away from the worst of the city lights, and let your eyes adjust for a while. Find the constellation Cassiopeia, that crooked W of stars hanging high in the northern sky. Slide your gaze south of it, toward the constellation Pegasus, and you will find a faint, oval smudge of light, softer than any single star, larger than your fingernail at arm's length. Most people who notice it assume they are looking at a nebula or a cluster of nearby stars, or some atmospheric quirk that will vanish if they look directly at it. They are not. They are looking at the Andromeda galaxy, a complete spiral system of roughly 1 trillion stars, and the light landing on their retinas at that exact moment is older than the entire human species. There is something quietly extraordinary about that little smudge. It is the single most distant object in the universe that an ordinary human eye, unaided by any telescope or camera, routinely picks up from a dark enough sky. Everything else you have ever seen with your naked eye, from the brightest planets to the most distant individual stars, sits inside our own Milky Way. Andromeda is the exception. It is the one thing in the night sky that lies outside our galaxy entirely, and it is the closest major galactic neighbor we have. There is nothing larger or comparable until you push outward by many more millions of light years. So you would think, if any galaxy in the universe might one day be within reach of human ambition, it would be this one, the closest, the brightest, the one that practically anyone, on any continent, can find with a slow sweep of the eye. And yet the title of this video is the claim it is. Andromeda will forever be out of reach. Not difficult, not a long shot, not a stretch. Forever, permanently, absolutely. The closest place in the universe outside our own galaxy is also one of the most permanently sealed-off destinations a human being could ever try to point a ship at. If that sentence feels like a contradiction, that is the right reaction, and the rest of this video is going to walk slowly through why the contradiction is real. There is not one reason. There is a cascade of them, and they reinforce each other. Distance is one, energy is another. The speed of light is a third, time itself is a fourth, biology is a fifth. The structure of space-time, in its strangest relativistic sense, is a sixth. The expansion of the universe is a seventh. The lifetime of the sun is an eighth. Each one of these, taken alone, would already make the journey to Andromeda impossible. Stacked together, they build a wall made of walls, and the wall reaches in every direction at once. There is something almost soothing about that kind of impossibility, once you stop fighting it. Most of the things we call impossible in everyday life are just expensive, or slow, or politically difficult. We secretly suspect that with enough effort and enough patience, someone, eventually, will figure it out. The journey to Andromeda is not that kind of impossibility. It is the other kind. The kind where the rules of the universe themselves refuse the request, and no amount of effort or patience changes the answer. The universe is not negotiating about Andromeda. The universe has already decided. Let yourself sit with the strangeness of the basic facts for a moment. The light reaching your eye from that faint oval smudge left Andromeda roughly 2.5 million years ago. On the Earth those photons departed toward, our ancestors were small bands of Homo erectus, walking the savannas of East Africa, having only recently mastered the deliberate control of fire. There were no modern humans yet. There was no Homo sapiens. There were no cave paintings, no agriculture, no writing, no spoken languages we would recognize. The photon landing on your retina tonight is older than every story your species has ever told, older than every word any human has ever spoken, older than the human species itself by an enormous margin, and it has been moving the entire time at 300,000 kilometers every second just to find your eye. That is what unreachable looks like, expressed as an arrival rather than a distance. Light, the fastest thing the universe allows, has been crossing this gap for the entire history of the human imagination, and it is still only just now showing up. But here is where the contradiction sharpens. Andromeda is not just sitting still at that distance. Andromeda is moving toward us. Of all the major galaxies in the sky, it is one of the very few whose light is shifted toward the blue end of the spectrum rather than the red, meaning it is approaching the Milky Way rather than receding. Modern measurements put its full three-dimensional velocity relative to our galaxy at around 300 kilometers per second. In about 4.5 billion years, the two galaxies will pass through one another for the first time. In about 6 billion years, they will merge into a single combined system. The destination is, in some literal sense, coming to meet us. So why, then, is unreachable still the honest word? Why isn't this just a long wait? The answer, which the rest of this video will slowly build, is that distance is only one of the walls. Time is another. Biology is another. The lifetime of the Earth is another. The mathematics of light speed is another. The geometry of spacetime is another. The behavior of every other galaxy in the universe is another. The destination's approach does not help if every other barrier remains in place. And every other barrier does remain in place. Andromeda's slow, immense gravitational drift toward the Milky Way moves at 300 kilometers per second, which sounds enormous, but in cosmic distances, it covers almost nothing in a single human lifetime. By the time the closing distance becomes meaningful, the Sun will already be in the early phases of its red giant transformation. The oceans of Earth will already have boiled off through a slow runaway warming, and any descendants of humanity that exist will be living in a solar system that has nothing recognizable left in it. So this is the question we are going to spend the next 2 hours pulling apart, one slow layer at a time. Why is the closest major galaxy in the sky also one of the most permanently unreachable places a human could try to go? What does it actually mean to call a destination unreachable when its photons land in your eyes every clear night, when its mass already pulls on yours, when its outer atmosphere already touches yours, and when the universe itself is, on the largest scale, pulling it toward you? Find a comfortable position. Let your shoulders settle. There is no urgency to any of this. The impossibilities we are about to walk through have been in place for billions of years, and they will be in place for billions more. You are not going to miss anything. The only thing this video asks of you is the slow patience to follow the chain of reasons until they all meet in the same place. The closest place humanity will never go is a strange thing to think about, and the strangeness only deepens the longer you sit with it. So let's start with the simplest of the walls, the one that does the most damage to intuition, the number, 2.5 million light years. We are going to take that number apart and see what it actually means. Because once you really feel it, the rest of the cascade begins to fall into place. Is less than break time equals 1s, is greater than number, part 2, the number that breaks intuition. The distance, written out in its modern, refined form, is 2,537,000 light years. Astronomers usually round it to 2.537 million. The figure has been hammered down over the last century by every method available to extragalactic astronomy, and it is one of the most thoroughly cross-checked distances in modern science. To know what it means, you first need to know what a light year is. A light year is the distance light travels in 1 year. Light, the fastest thing the universe permits, moves at 300,000 kilometers per second. That is roughly the distance from Earth to the Moon in 1¼ seconds. It is roughly the distance from Earth to the Sun in 8 minutes. Pile up enough of those seconds, the way you pile up grains of sand into a mountain, and in 1 year light covers a distance of about 9.5 trillion kilometers. 9.5 million kilometers. A number with 12 zeros after it. That is 1 light year. Now stack 2.537 million of those, end to end. Each one already a number with 12 zeros in it, and now multiplied by a number with 6 zeros in it. The product is something almost laughable. 24 quintillion kilometers, give or take. A 2 followed by 19 zeros. It is, in raw kilometers, the kind of number you cannot really hold in your head. Numbers above, about 1 billion, stop meaning anything in human intuition. The brain simply files them under huge, and the difference between a quadrillion and a quintillion stops registering. This is the problem astronomy creates for honest narration. The numbers are so far past human intuition that they have to be translated back into something a body can feel. Otherwise, they slide off the listener as easily as they slid off the page. So let's slow down and translate. The number got its modern form because Edwin Hubble, in the early 1920s, did something quietly revolutionary. He pointed the Hooker telescope on Mount Wilson at what was then known as the Andromeda Nebula and looked for a specific kind of variable star inside it. Cepheid variables, named after the prototype star in the constellation Cepheus, change in brightness with absolutely regular timing. Their period of pulsation directly tells you their intrinsic brightness, and from intrinsic brightness compared to apparent brightness, you can calculate distance. It is one of the cleanest tools astronomy has ever invented for measuring across cosmic gaps. Hubble's measurement, published in 1924, demonstrated for the first time that the Andromeda Nebula was not a cloud of gas inside our galaxy. It was an entire separate galaxy, roughly comparable in size to our own, sitting at a distance so enormous that it lay outside the Milky Way completely. The single observation changed the size of the known universe by a factor of millions overnight. Before Hubble, most astronomers thought the Milky Way was the whole universe. After Hubble, the Milky Way was one of countless galaxies in a universe billions of light years across. The Andromeda distance has been refined many times since. Cepheid variables continue to be used. Type 1a supernovae have been added as standard candles. Eclipsing binary star pairs have provided independent confirmations. The tip of the red giant branch, a specific point on the brightness ladder of old stars, gives another check. The Gaia spacecraft, launched in 2013 and delivering data through the 2010s and into the 2020s, gave parallax measurements of incredible precision for nearby stars, anchoring the distance scale. And the James Webb Space Telescope, since its first observations in 2022, has produced increasingly detailed near-infrared imagery of Andromeda's bulge and disk that further pin down the distance. Through all of these methods, the answer keeps converging on about 778 kiloparsecs, which translates to 2.537 million light-years. The error bars on that figure are now well under 2%. We know the distance to Andromeda better than humanity has ever known the distance to any object outside the Milky Way of comparable scale. Now, let's anchor the number in something a body can feel. The fastest spacecraft humans have ever sent into interstellar space is Voyager 1, currently moving away from the Sun at roughly 17 kilometers per second. Voyager 1 was launched in 1977. It has been moving for nearly 50 years, and in that time it has covered about 25 billion kilometers from Earth. That sounds enormous. It is, by every measure of human engineering, an extraordinary achievement. And yet, scaled against the distance to Andromeda, it is essentially nothing. If you sent another Voyager 1 toward Andromeda today, at the same speed Voyager 1 is currently traveling, the journey would take roughly 46 billion years to complete. 46 billion years. The current age of the universe, from the Big Bang to right now, is about 13.8 billion years. The Voyager 1 trip to Andromeda is more than 3 times the age of everything. By the time the spacecraft would arrive, the universe would have aged from its current adolescence into a far future state in which most of the stars currently burning in the sky would have long since exhausted their fuel. Let's try another scale. Imagine you shrink 1 year of light travel down to 1 millimeter on a desktop. Just 1 millimeter. At that scale, the Sun is about 8 millimeters from Earth, which is barely a finger's width. The nearest star, Proxima Centauri, sits 4.24 millimeters down the desk. The Milky Way, end to end, would stretch about 100 meters the length of a soccer field, and Andromeda, in the same shrunk-down scale, sits 2.5 kilometers away, across town, on a different street, in a different neighborhood. Light, the fastest carrier the universe permits, takes 2.5 million years to make that walk. There is one more anchor that I think makes the distance the most vivid. Imagine, for a moment, that the entire Milky Way is the size of a dinner plate sitting in front of you. The Sun is a single dust mote somewhere on the plate. Earth is invisible to any imaginable resolution. Andromeda, scaled to the same dinner plate Milky Way, would be another dinner plate sitting about 3 meters away. 3 meters. The space between the two plates would be enormous compared to either plate, but small compared to the rest of the universe. Most galaxies in the visible universe, scaled to that picture, would be hundreds or thousands of meters away. Andromeda is uniquely close, and it is still completely out of reach. That uniqueness is worth dwelling on, because it sets up the rest of the cascade. Andromeda is not the easiest cosmic destination, because we have not gotten lucky elsewhere. It is the easiest because of basic cosmic geography. There simply is no other major galaxy of comparable size that is closer to us. The Magellanic Clouds, the large and the small, are closer, but they are not independent galaxies of comparable size to our own. They are satellite galaxies of the Milky Way, much smaller and gravitationally bound. They are essentially extensions of our own galactic neighborhood, not separate destinations in the same sense. The first true peer galaxy, the first one that stands on its own as something like the Milky Way's twin in size and shape, is Andromeda. Everything else of comparable scale is much further away. So when we talk about Andromeda being unreachable, we are not saying the easy ones are taken and only the hard ones remain. We are saying the best case is impossible. The closest peer galaxy in the universe is, by every measure available to physics and engineering, beyond human capacity to ever visit. Whatever conclusions the rest of the video draws, you can apply that same conclusion, only stronger, to every other galaxy in the universe. Andromeda is the easiest of the hard ones, and even Andromeda is foreclosed. The strange part is that knowing this, in greater detail than ever before, does not bring it any closer. The James Webb Space Telescope's images of Andromeda, refined through 2024 and into 2025, are the most beautiful and detailed maps of that galaxy that anyone has ever made. We can resolve individual stars in its disk. We can pick out the dust lanes and the embedded young clusters of forming stars in its spiral arms. We can map the diffuse gas in its halo through quasar absorption surveys. We can model its motion against the Milky Way with unprecedented precision. And the gap between us has not shrunk by a single meter. Knowing exactly where Andromeda is in greater detail than at any other moment in history, only makes the unreachability more vivid. We can see the destination in fossil light, in extraordinary clarity. We cannot go. So if distance alone were the wall, you could imagine a solution. You could imagine some far future civilization with engines we cannot dream of, with energy budgets and propulsion systems that make ours look like primitive smoke signals. You could imagine them eventually crossing the gap. But Andromeda has more than one trick. The destination is moving toward us. And that fact, far from making the trip easier, opens up the strangest paradox in this whole story. Because the destination is approaching on a cosmic timescale, and yet that approach makes the trip not closer, but actually stranger and more impossible. We turn next to the galaxy that is coming for us. Is less than break time equals 1s, is greater than number. Part 3. The galaxy that is coming to us. When you point a telescope at almost any object in the sky, outside the local group, the light coming back is stretched. The wavelengths of all the lines in the spectrum, the bright lines from hydrogen, the absorption bands from heavier elements, are shifted toward the red end. This is the redshift, the signature of cosmic expansion, the discovery that allowed Hubble to figure out that the universe itself is growing. Almost every galaxy is moving away from us, and the further away it is, the faster it recedes. Andromeda breaks this pattern. Its light is shifted blue. The wavelengths come back compressed rather than stretched. Andromeda is approaching the Milky Way. The two galaxies, against the backdrop of cosmic expansion, are moving toward one another. The radial velocity, the rate of approach along the line of sight between us and Andromeda, has been measured for over a century and now stands at about 110 kilometers per second. That sounds extraordinary at first. 110 kilometers every second, roughly 400,000 kilometers per hour, toward us, continuously, for as long as anyone has been looking. But of course, against the distance of 2.5 million light-years, even 400,000 kilometers per hour is essentially nothing in any reasonable human timeframe. To close the gap between Andromeda and the Milky Way takes billions of years, even at that speed. The cosmic clock and the human clock are not on the same scale. The transverse velocity Andromeda's motion across our line of sight, rather than along it, was harder to measure for a long time. You cannot use the spectral shift for sideways motion. You have to actually watch the galaxy move across the background of even more distant stars over decades. The Gaia spacecraft's second data release in 2019 gave us the cleanest measurement of this transverse motion to date, and it surprised astronomers. Andromeda is moving sideways, more than long popularized models had assumed. Combined with the radial approach, the full three-dimensional space velocity of Andromeda relative to the Milky Way comes out to roughly 300 kilometers per second. That number is what astronomers feed into their merger models. And the models, refined over the last decade, paint a picture of what is coming. In about 4.5 billion years, the central regions of Andromeda will sweep through the outer regions of the Milky Way for the first time. It will not be a single neat impact. It will be a glancing first pass, where the two galaxies move through one another like two cyclists meeting at a wide intersection from oblique angles. Stars from each galaxy will be pulled into long tidal streams, stretching for hundreds of thousands of light-years. Gas clouds will collide and compress, triggering enormous waves of new star formation across both systems. The shapes of both galaxies will distort dramatically. After the first pass, the two galaxies will separate again, pulled apart by their own momentum, but bound now by mutual gravity. They will recede from each other for a while, then return. The second close pass will occur perhaps 1 billion years after the first. The dance will continue, with each pass progressively tightening the orbital embrace, until the two cores spiral into one another and merge. The final settled configuration predicted to occur roughly 6 billion years from now, is a single combined galaxy, an elliptical, no longer two spirals. Astronomers have given this hypothetical future galaxy a name. The most popular version is Milkomeda, though some prefer Milkdromeda. The supermassive black holes at the centers of each galaxy, Sagittarius A star at our center, and M31 star at Andromeda's, the latter of which is roughly 50 times more massive, will themselves merge in a final climactic event, releasing a burst of gravitational waves that would shake spacetime across the cosmos. So if all of this is happening, if the destination is genuinely coming to meet us, why is unreachable still the right word? Doesn't the approach itself solve the problem? Don't we just wait? This is where the deeper layers of the cascade begin to bite. The wait is too long. The lifetime of the sun is too short. The lifetime of Earth's habitable phase is much shorter than that. By the time the 4.5 billion year first pass occurs, the sun will have brightened enough through its slow main sequence aging that Earth's oceans will have boiled off in a runaway warming somewhere around the 1 billion year mark. The face of the planet we know will be gone 3.5 billion years before the merger even starts. And even if you imagine humans somehow surviving that a stretch beyond plausible, the sun itself enters its red giant phase around the 5 billion year mark, expanding past Earth's current orbit and rendering the inner solar system uninhabitable. The destination is coming. But there is no future in which a human, descended from us, stands on a planet around the sun and watches Andromeda's stars become close enough to map. The Earth we live on cannot wait that long. The sun we orbit cannot wait that long. The species we are cannot wait that long. There is a second reason the approach does not solve the problem, and it has to do with what a merger of two galaxies actually means. We are used to the word collision, implying things smashing into each other. We picture two cars meeting, two ships meeting, two planets meeting. In all those cases, two solid objects with edges come into contact and shatter or fuse. A galactic merger is not like that at all. The galaxies are mostly empty space. The Sun's nearest neighbour, Proxima Centauri, is 4.24 light-years away. That is 40 million billion kilometres between two stars. Stars in the disk of a galaxy are spread out over distances that, compared to the size of the stars themselves, are absurdly enormous. Imagine each star as a grain of sand and ask how far apart the grains are. The answer is roughly the distance between cities. When two galaxies merge, individual stars almost never collide. The chance of any two stars actually impacting one another during the entire merger is, statistically, vanishingly small. What happens instead is that the gravitational fields of each galaxy distort the orbits of the other galaxy's stars. The two flocks of stars interweave, pass through one another like two flocks of birds whose paths cross and reorganize their orbits. The gas, which is much more diffuse and continuous than the stars, does collide, and that is where the bursts of new star formation come from. But the stars themselves mostly slide past each other into new patterns. This matters because it changes what arrival means. If a human somehow made it across the gap and showed up at the center of Andromeda 4.5 billion years from now, just as the merger was beginning, they would not arrive at a planet on a beach with the words "Welcome to Andromeda" carved into the sand. They would arrive somewhere in a sprawling, diffuse field of stars. The stars near them would belong to Andromeda. The stars further away would still be in the Milky Way. The boundary between the two galaxies would have become meaningless. The destination, in any geographic sense, would have already started to dissolve. There is no there to arrive at. The destination is not a place. It is a swirling cloud of stars, which over billions of years rearranges itself into a new configuration entirely, and the new configuration is neither Andromeda nor the Milky Way, but a third thing made out of both. There is one more wrinkle worth noting, because it sharpens just how unsettled the merger picture still is. A 2024 analysis using updated Gaia and Hubble data argued that the probability of an actual merger within the next 10 billion years is closer to 50% than to certainty. The galaxies may glance off each other repeatedly without fully binding, depending on the precise three-dimensional motions and on the gravitational influence of nearby smaller systems. The merger we have been describing for decades may be one possible outcome, not an inevitability. The exact future of the local group is being refined every few years as new data comes in. And there is the M33 problem. The Triangulum galaxy, the third largest member of the local group, has likely already had a close encounter with Andromeda within the last few billion years, leaving signatures of past tidal disturbance in both galaxies. The future merger may not be a clean two-galaxy event, but a three-galaxy interaction, with M33 potentially joining or being absorbed before the main collision plays out. So the destination is approaching. The destination is changing shape. The destination is not even certainly going to merge with us in the way the popular picture has long suggested. And the destination, when it arrives, if it arrives, is not a place a human can stand on. The approach does not save the trip. The approach makes the trip stranger. Here is the truth the rest of this video will keep returning to. Andromeda is not unreachable because we have not tried hard enough. Andromeda is unreachable because the universe itself, in every direction we examine, has placed a barrier. The distance is one. The biology is another. The physics of light speed is another. The geometry of spacetime is another. The lifetime of the sun is another. The expansion of everything outside the local group is another. The very fact that the destination is moving rather than fixed, and that its motion does not actually bring there closer in any usable way, is yet another. We are going to walk into the next barrier now. The wall that physicists know best, and the one that places the absolute ceiling above every conceivable travel scheme. The speed of light and the energy wall it builds is less than break time equals 1s, is greater than number, part 4. The light barrier and the energy wall. In 1905, in a small apartment in Bern, Switzerland, a 26-year-old patent clerk named Albert Einstein published the paper that would quietly reorganize how everyone understood the universe. The paper introduced what we now call special relativity, and at its center was a single, strange claim. The speed of light is not just a number, it is a structural property of the universe itself. Every observer, no matter how they move, measures light moving at the same speed, and no object with mass can ever reach that speed, let alone exceed it. That was a deeply counterintuitive claim, and it took years before the scientific community fully absorbed its implications. But it has been tested in countless experiments over the more than a century since, and the answer is always the same. The universe has a maximum speed. Light moves at that speed. Anything with mass cannot match it, and the closer you push toward it, the harder pushing becomes. The math is straightforward to state, even if the implications are not. As you accelerate any massive object closer and closer to the speed of light, the energy required to add even a tiny bit more velocity grows without limit. To reach half the speed of light requires substantial energy. To reach 90% requires much more. To reach 99% requires far more than that, and the curve goes asymptotic. The energy required to actually reach the speed of light becomes infinite, not extremely large, infinite. There is no possible energy supply, no matter how clever, that could carry a massive object across that final line. This is not an engineering limitation that some future civilization might solve. It is the structure of space-time. The speed of light is the ceiling, because the geometry of the universe makes it the ceiling. Any travel plan we make, today or in any imaginable future, has to live underneath it. Now apply that ceiling to Andromeda. The distance, as we have established, is 2.5 million light-years. Even at the speed of light itself, physically impossible for any massive object. But useful as a thought experiment, the trip would take 2.5 million years, measured by clocks at the Earth end. There is no faster journey. The universe forbids it. So immediately, we have a stark answer to the basic question. Even with hypothetical engines that could push us to within a hair's breadth of the speed of light, the minimum one-way travel time, measured from Earth, is 2.5 million years. The civilization that launches such a mission has to be willing to wait 2.5 million years for arrival, and another 2.5 million for any signal of arrival to come back. 5 million years of round-trip wait, and that is the best case under the most generous assumptions physics permits. For comparison, the entire span of recorded human civilization, from the first cuneiform tablets in Sumer to right now, is about 5,000 years. The trip would take 1,000 times the entire span of human civilization just for arrival, and 2,000 times that span for confirmation. No human institution has ever survived for 2.5 million years. No language, no religion, no nation, no empire. The very concept of a civilization that launches and waits presumes a kind of continuity that no human structure has ever demonstrated. We are not talking about a long mission. We are talking about a mission whose duration exceeds the survival horizon of every cultural form humans have ever built by orders of magnitude. That is the speed of light side of the wall. Now we turn to the energy side. The relationship between velocity and energy for accelerating any mass is captured by an equation that engineers call the rocket equation, originally formulated by the Russian theorist Konstantin Tsiolkovsky in the late 19th century. The equation says that the velocity change a rocket can achieve depends on how much fuel it carries and how fast that fuel exits the engine. The trouble is that the relationship is exponential. To go twice as fast, you do not need twice as much fuel, you need many times more. And to go 10 times as fast, you need a number that becomes ridiculous very quickly. For chemical rockets, the kind we use today, the rocket equation makes interstellar travel impossible before you even leave the solar system. The fastest chemical rockets reach about 1/10,000th the speed of light. At that pace, the trip to Andromeda takes 25 billion years, nearly twice the current age of the universe. For fusion rockets, hypothetical engines that burn hydrogen isotopes, the way the sun does the math is better. A well-designed fusion engine could in principle reach perhaps a few percent of the speed of light. Even at 10% of light speed, which is wildly optimistic for any fusion technology we can describe today, the trip to Andromeda takes 25 million years. For antimatter, rockets' engines that turn matter directly into energy with 100% efficiency, the math is better still. Theoretically, you could reach a substantial fraction of light speed, but there is a problem. We cannot produce antimatter in any useful quantity. The total amount humanity has ever produced across every particle accelerator on Earth is measured in nanograms. Powering a spacecraft to Andromeda would require many tons. There is no known way to generate, store, or contain that much, and antimatter explodes on contact with normal matter in a single uncontrolled flash. Even setting all of these problems aside, the energy budgets remain absurd. Consider a 1 kilogram payload, just a single kilogram. Accelerating it to half the speed of light requires roughly 10 to the 16th power joules, comparable to the total energy released by detonating 2.4 million Hiroshima-scale bombs. And that is only the acceleration. To decelerate at the other end, because otherwise you sail past Andromeda at half-light speed and disappear into intergalactic space, you double the budget. Roughly 5 million Hiroshima bombs for 1 kilogram, one way. Scale up to a meaningful crewed mission. A small habitat, capable of supporting a crew, would weigh hundreds of tons at minimum, probably thousands. The energy budget scales linearly with mass. We are talking about energy requirements that exceed humanity's total cumulative energy production since the invention of fire by many orders of magnitude for the kind of payload that would actually serve as a vehicle for human beings. This is where the ambitious proposals come in. The most aggressive, realistic, interstellar travel concept currently on paper is Breakthrough Starshot, originally announced in 2016 and still in laboratory and proof-of-concept stage as of 2025. The proposal is to send gram-scale probes, essentially tiny chips with sensors and communications hardware, accelerated by ground-based lasers to 20% of the speed of light. By making the payload tiny and by leaving the propulsion energy on the ground rather than on board, the math becomes much more tractable. The probes can, in principle, reach Alpha Centauri, 4.24 light-years away, in about 20 years at that velocity. Now scale Breakthrough Starshot to Andromeda. At 20% the speed of light, the trip to Andromeda is 12.7 million years. Not 12,000, not 1,200,000, 12 million years. And that is for a gram-scale probe with no life support, no propulsion mass at the destination, no way to slow down on arrival. The probe arrives at 20% the speed of light, sails past Andromeda in a matter of weeks, and continues on into intergalactic space. There is no rendezvous, there is only a flyby, 12 million years after launch, at a velocity so high that the probe interacts with the destination galaxy only briefly before continuing onward. Even at this most aggressive, realistic plan, the trip is 12 million years for a single chip-scale device with no ability to stop. There is no version of Breakthrough Starshot that delivers anything resembling a crewed mission to Andromeda. There is barely a version that delivers a working probe. There is one more constraint on relativistic travel that often gets overlooked. Space is not actually empty. It contains thin gas, mostly hydrogen at densities, that, while extraordinarily low by terrestrial standards, are significant for a spacecraft moving at a sizable fraction of the speed of light. At half the speed of light, a single hydrogen atom impacting a spacecraft delivers the energy of an X-ray photon. A spacecraft moving through interstellar space at relativistic speed becomes a relativistic sandblaster of itself. The forward-facing surfaces of the ship are bombarded continuously by atoms moving toward it at near light speed, and the energy of these impacts is enormous in aggregate. Shielding against this kind of bombardment is itself an enormous engineering problem. Solutions have been proposed: magnetic shields, ablative armor, drone shields flying ahead of the main ship, but all of them add mass, which makes the rocket equation worse, which requires more energy, which makes the energy wall even more absurd. The shielding problem is real, and it tightens an already impossible budget further. The conclusion that physics offers, at the end of all this, is bleak in its clarity. The speed of light is the universe's maximum speed, and Andromeda is 2.5 million light-years away. Even at light speed, the trip is 2.5 million years. No engine, no matter how cleverly designed, can do better. And the energy required to actually reach a meaningful fraction of light speed for any meaningful payload vastly exceeds anything humanity could ever marshal. The walls are not engineering walls. They are physics walls. The cosmos does not permit a better answer. But physics, having shut one door, leaves what looks like an open window. The window is time itself. Einstein's same relativity, that places the speed of light as an absolute ceiling, also offers something strange. The faster you go, the slower your own clock ticks. A trip that takes 2.5 million years measured by Earth's clock could, in principle, take only thousands of years measured by the traveller's clock. So maybe there is a way to compress the experience of the trip even if the trip itself remains long. This is the shortcut that looks like an escape. It is also, when you look at it closely, the cruelest of the walls. It compresses the traveler's experience while leaving home behind forever. Let's walk through it. Is less than break time equals 1s is greater than number, part 5. Time dilation, the shortcut that costs you everything. The physics of moving clocks has been confirmed in countless experiments over the last 100 years. The simplest version is this. Place 2 identical atomic clocks side by side and synchronize them. Take one of them on a long, fast airplane flight while leaving the other on the ground. When the flying clock comes back, it reads slightly less time than the ground clock. Not because the flying clock is broken, because moving clocks genuinely tick slower than stationary ones. The effect was measured in 1971 in the Hafele-Keating experiment, and it has been confirmed at increasing precision every decade since. Even your GPS satellites have to correct for this every second to keep their positions accurate. Without the correction, GPS would drift off by kilometers within a day. At ordinary speeds, the effect is tiny. At a few hundred kilometers per hour, the difference between moving and stationary clocks is measured in nanoseconds per hour. But the effect grows as you approach the speed of light. At 10% of light speed, moving clocks tick at about 99.5%. The rate of stationary clocks, a difference of about 1 part in 200. At half the speed of light, moving clocks tick at about 87% the rate of stationary ones. At 90% of light speed, moving clocks tick at about 44%. The interesting region is closer to the ceiling. As you push past 99%, the slowdown accelerates dramatically. At 99.9999% of the speed of light 5 nines after the decimal, the time compression factor is roughly 707. A moving clock at that speed ticks about 700 times slower than a stationary one. Apply this to the Andromeda trip. At 99.9999% of light speed, the subjective travel time for someone on board would be the Earth time of 2.5 million years, divided by 707. The arithmetic comes out to roughly 3,500 years, a bit less than the time from the construction of the Egyptian pyramids to today. That is, on the face of it, an extraordinary shortcut. A trip that physics says cannot take less than 2.5 million years from Earth's frame becomes, for the traveller, a trip of 3,500 years. Still long. Still longer than any human lifetime. But suddenly, tractable on civilizational timescales. A society of people committed to multi-generational travel could in principle survive 3,500 years where they could not survive 2.5 million. Now let's tighten the trap. The trip is only 3,500 years for the traveller. 2.5 million years still pass on Earth. The civilization that launched the mission, the families and cultures and governments and species that sent the travellers off, all continue to exist in their own frame, and all of them experience the full 2.5 million years. By the time the traveller arrives, the Earth they left is gone, not just changed, gone. 2.5 million years of evolution, geology, climate change, and cosmic accident separates the Earth at launch from the Earth at arrival. To put that number in perspective, 2.5 million years ago on Earth, Homo erectus was the most advanced human-related species. The genus Homo was just beginning to walk the planet. Modern humans had not yet evolved. Everything we are, as a species, every language, every technology, every culture, every nation, every art form, every body of knowledge, emerged within the last 2.5 million years. So 2.5 million years from now, on the Earth side of the launch, anything could happen. Modern humanity could be long extinct. New species could have replaced us. The species replacing us could itself have come and gone. Civilizations of unimaginable nature could have risen and fallen many times. The traveller is gone for an interval of Earth time longer than the entire history of the human species. They cannot send messages back during the trip light traveling at the speed limit, cannot catch up to them. They cannot return without making the same trip again in the other direction, adding another 2.5 million years of Earth time to the round trip. There is no contact. There is no homecoming. There is no civilization waiting to greet them. And the destination they arrive at is not the Andromeda they set out to visit. The light that left Andromeda the moment they launched took 2.5 million years to reach Earth. And during that 2.5 million years, the traveler was crossing the gap at near light speed. So the traveler arrives in an Andromeda that has aged an additional 2.5 million years past the Andromeda their telescopes observed before launch. They cannot study the Andromeda they meant to study. They can only study its future. The stars they catalogued before launch have moved. Some have exploded as supernovae. Some have been disrupted by other interactions. The galaxy, as it existed at launch, is invisible to them on arrival. They see only the version that has aged 2.5 million years past that. Connect this back to the central thread directly. Time dilation does not break the wall between us and Andromeda. It compresses the traveler's experience, but leaves the universe's clock running at full speed on the home end. The journey, in real cosmic time, still takes 2.5 million years. The traveler is just a small subsystem riding through that time on a compressed personal scale. Everything else, Earth, the Sun, the human species, the destination galaxy itself, continues on its own clock and arrives at the rendezvous in its own future. There is something almost cruel about this. Relativity holds out what looks like a solution to the longest of the journey's barriers. And then, once you look closely, you realize the solution doesn't actually remove the barrier. It only removes the time's traveler's perception times of the barrier. The universe itself is unmoved. The home end of the trip pays the full price in real time, regardless of how fast the traveler's clock runs. There is also the energy problem from the previous part, which gets worse, not better, in this scenario. Reaching 99.9999% of light speed requires energy that is dramatically higher than even the half-light speed budget we discussed. The energy goes up rapidly as you approach the ceiling by the same exponential math that defines the rocket equation. A spacecraft moving at 5/9 of light speed requires roughly 500 times more energy per unit mass than a spacecraft moving at half-light speed. So the energy wall, far from being mitigated by time dilation, is intensified. And there is the philosophical wrinkle worth pausing on. Imagine you are the traveler. You spend 3,500 years aboard a ship moving at near light speed. Your time on board runs at full subjective rate. You age, you sleep, you eat, you read, presumably. You see Earth fall behind, see the sun shrink to a single bright point, and then to a star among the millions, see the rest of the Milky Way slide past as the ship climbs out of the galactic plane. Your time runs normally on board. The ship is your full reality, and every minute of your time is, somewhere out there, hundreds of years of Earth time. Every breath you take, civilizations rise and fall behind you. Every page you turn, your descendants are born and die and forgotten. The home that launched you ceases to exist before you finish your first month. The species that bore you may not survive a year of your trip. The civilization that funded the mission, that planned the route, that designed the ship, has no continuity with whatever exists at Earth when you arrive. The arrival, then, is not an arrival in any meaningful social sense. The traveler is not a delegate from a known civilization to an unknown one. The traveler is the last and only representative of a species that, by the time of arrival, may not exist at all. They are a fossil of their own people, arriving at a fossil of a destination, 2.5 million years displaced from both, with no way to communicate back to either origin or to anyone they will ever know again. This is what relativity offers as the shortcut. It is not a shortcut. It is a one-way passage out of every connection the traveler has ever known. The universe does not let you cheat distance. It only lets you cheat times your own perception of duration, and the cheating costs you everything you came from. Call back to the central thread. Time dilation does not break the wall. It only changes which wall holds. You can compress your experience, but you cannot compress the universe's. Andromeda's distance is denominated in times Earth's, times time, and Earth never gets its time back. The destination remains, by every measure that matters, beyond human reach. The traveller can arrive in their own subjective frame, but they cannot ever return, cannot ever report back, cannot ever be part of any continuing human story. The you that arrives in Andromeda is, in every sense that matters, no longer connected to the us that sent them. The wall holds. So the speed of light is the ceiling, and the energy wall is the floor, and time dilation is the cruel staircase that lets the traveller ride through compressed time at the cost of every human connection. There is, in principle, another approach. You could accept the long duration and build a vessel that carries humans across it slowly, a generation ship. Many generations of crew live and die aboard, with the descendants of the original launch crew arriving at the destination thousands or millions of years later. This is the romantic image of interstellar travel that science fiction has carried for nearly a century. Let's see what physics and biology have to say about that. Is less than break time equals 1s is greater than number, part 6. Biology was never going to make it. The generation ship is, in a sense, the answer to time dilation's cruelty. If the traveller cannot return, and if compressing their own time only deepens the disconnection from home, why not skip the relativistic travel altogether? Why not build a slow-moving vessel, a sealed habitat, and let successive generations of crew live aboard, with the descendants of the original launch crew eventually arriving at the destination? The original travellers don't make it, but their great many times great-grandchildren do. The civilization that launches the mission can persist on Earth for as long as it persists, and the mission, on its own slower timescale, proceeds independently. The idea has a long history in science fiction. The first novel-length treatments of generation ships appeared in the 1940s. Robert Heinlein's Universe, published in 1941, told the story of a generation ship whose crew had forgotten they were on a ship at all. Brian Aldiss's Non-Stop, in 1958, did something similar. The trope has been refined countless times since, and it persists because it answers what looks like an emotional version of the interstellar problem. The trip is long, so make the ship a complete world, and let humans live on it as a complete world for as long as the trip takes. Apply this to Andromeda. At 10% of the speed of light, the trip to Andromeda takes 25 million years. At 1%, 250 million years. At 0.1%, still 10 times faster than anything we can currently build, 2.5 billion years. Let me say those numbers more slowly. The minimum plausible duration of a generation ship trip to Andromeda is on the order of 25 million to a few hundred million years, possibly longer. The math does not care whether you think of the trip in those terms. The trip is what it is. To get a sense of what kind of time those numbers represent, consider what was happening on Earth 250 million years ago. That puts us well into the Permian period, before the great extinction at the end of the Permian wiped out roughly 90% of marine species and 70% of land species. The largest land animals were synapsids, the proto-mammals that preceded the dinosaurs, animals with sprawled-out limbs and reptilian skulls. Birds did not exist. Flowering plants did not exist. Mammals, as we know them, did not exist. The continents were assembled into a single supercontinent named Pangaea. The world was almost unrecognizable. That is the kind of duration a generation ship to Andromeda, at 1% of the speed of light, would need to survive as a sealed system. 250 million years of continuous operation, with successive generations of crew born, living, and dying on board, with the ship's ecosystem cycling all the carbon, nitrogen, oxygen, water, trace minerals, and food crops that the crew needs to live, with the ship's mechanical systems continuing to function, with the social structures of the crew remaining intact. Let's walk through what we know about closed ecosystems. The most ambitious experiment in closed ecology that humans have ever attempted was Biosphere 2, a 1.3-hectare sealed structure in the Arizona desert, designed to house 8 people for 2 years in a complete recreation of the Earth's major ecosystems. It was the most expensive and best-engineered closed ecology experiment ever attempted, and it had access to all the engineering expertise that early 1990s America could provide. Biosphere 2 ran for 2 years, from 1991 to 1993, and it did not really work. Oxygen levels inside the structure declined steadily as the soil microbiology consumed oxygen faster than the plants could produce it. Carbon dioxide levels fluctuated wildly. Cockroaches and ants thrived. Most other species struggled. Most of the vertebrate species died. The crew became hungry. By the end of the 2 years, supplemental oxygen had to be pumped in from outside to keep the crew alive. A second mission, from 1994 to 1995, ended early due to financial and management problems. The experiment was eventually rebranded as a research facility rather than a closed ecology demonstration. The lesson Biosphere 2 delivered was sobering. Even with the full engineering attention of a wealthy society, even on a 1.3-hectare scale with 8 people for 2 years, sealing a slice of biosphere produced something that could not maintain itself. Now imagine scaling that experiment to a ship carrying, say, several thousand people. The minimum number geneticists have estimated would be required to maintain enough genetic variability to avoid catastrophic inbreeding over hundreds of generations across 250 million years. The challenge is not just engineering. It is biology in dimensions we have never tested. Consider the genetic drift problem. In any small population, generation by generation, the gene pool changes randomly. Rare alleles disappear. Common alleles can become fixed or can drift to extinction. Over many generations in a small isolated population, this drift becomes substantial. Over 100,000 generations, the kind of timescale we are talking about, for a multi-million-year trip, the population's genome would diverge from the launching population in ways that cannot be predicted or controlled. Whoever arrives is not, in any genetic sense, the descendant of humans as we currently know them. They are something else, a new and unpredictable species that happens to share an ancestor with us a great many generations back. Consider the mutation problem. Cosmic rays, even in interstellar space, would penetrate the ship's hull continuously. Every passing year, every passing decade, every passing century would deposit mutations in the crew's DNA. Most mutations are harmful or neutral. Some, accumulating over geological time, would shift the population's biology in ways we cannot foresee. The crew of 100,000 years from launch would be biologically different from the crew at launch, and not in ways anyone could plan for. Consider the social problem. The crew at launch volunteers. The crew thousands of generations later does not. They are born into a sealed environment they did not choose, on a mission they did not sign up for, bound to a destination they may or may not believe in. Multiple sociology studies of much shorter duration in closed environments, Antarctic stations, submarines, simulated Mars missions suggest that human psychology becomes increasingly difficult to manage as the duration of confinement grows. The longest continuous closed environment human experiment has been the International Space Station, with crews rotating every several months. Even there, multi-month stays produce measurable psychological strain. A multi-million-year mission with permanent population would face problems we have no analogue for. Consider the cultural problem. The mission's purpose at launch is to reach Andromeda. The reasons for that purpose, the cultural framing, the scientific motivation, the social agreements that made the launch possible, would not survive intact through 100,000 generations of population change. By the time the descendants of the launching crew reach the destination, the original mission may be a half-remembered cultural artifact, or may have been forgotten entirely, or may have been rejected by the descendants as something they did not ask for. Consider the simple fragility of any closed system. Imagine running any modern building for 10,000 years without external resupply or repair from outside. Even the most robust structures we have ever built, the pyramids of Giza, the Great Wall, the Roman aqueducts, degrade significantly over thousands of years, even with continuous human maintenance. A sealed ship for 250 million years would have to maintain itself with internal labor and internal resources without ever resupplying from outside. The materials engineering alone exceeds anything we currently know how to do. Consider that this is the minimum trip duration. We have been talking about 10% or 1% of the speed of light. Those speeds are wildly beyond anything we currently know how to achieve for a vehicle of meaningful mass. A more realistic propulsion concept might top out around 0.1% of light speed, or even lower. At those speeds, the journey extends to billions of years. The continuous operation of a sealed human ecosystem for billions of years is so far beyond the survival horizon of anything we know how to engineer that the proposal stops being a plan and becomes a fantasy. Connect this back to the central thread directly. The energy and light speed walls said the trip cannot be funded or accelerated. Time dilation said the trip cannot be returned from. Biology now says the trip cannot be survived in the slow form either. Each wall is independent. Each is sufficient on its own. Together they make Andromeda not just impractical, but, in every direction we examine, impossible. There is one further uncomfortable detail worth mentioning, which is that even if a generation ship somehow worked, even if all the engineering, biology, social, and cultural problems were solved, the destination at arrival would not be the one anyone planned for. Andromeda will not stand still during the trip. It will move 300 kilometers per second toward us, and toward whatever direction its motion takes it through space. Stellar populations will evolve. Planetary systems will continue to develop and decay. The Andromeda the descendants arrive at is not the Andromeda their ancestors launched toward. The destination has aged hundreds of millions of years, so we have walked through several walls now: distance, energy, the speed of light, time dilation, biology. 5 separate forms of impossibility, each enough to foreclose the trip. And yet, we are only partway through the cascade. The next set of walls is the strangest of all. They are not about how to get to Andromeda. They are about what Andromeda actually is. Because Andromeda is not a single fixed place in space. It is not even a single fixed place in time. And in a real, measurable physical sense, the diffuse outer atmosphere of Andromeda is already touching us right now, mingled with the outer atmosphere of the Milky Way in a contact that has already begun and that we cannot stop. The next act walks into those stranger barriers, is less than break time equals 1s, is greater than number, part 7. Andromeda is already touching us. Hold in your mind the picture we have been building. 2 distant points in space, 2.5 million light-years apart, separated by an enormous gulf of essentially empty space. That picture is what most of us carry around when we think of Andromeda. The Milky Way over here, Andromeda over there, a great gap between them. That picture is wrong. The galaxies, as visible structures, are spirals roughly 100,000 and 220,000 light-years across, respectively. That much is accurate. But each galaxy is wrapped in something else. Each spiral disk is surrounded by an enormous diffuse halo of gas, much fainter than the disk, much harder to detect, but enormous in extent. The halo is not invisible to careful observation. It absorbs and re-emits light at specific wavelengths, and you can map it by looking at how it affects the light of more distant objects passing through. The Hubble Space Telescope's Project Amiga, the absorption map of ionized gas in Andromeda, has done exactly this kind of mapping. Originally published in 2020 and refined through several follow-up papers since, the project used the ultraviolet light of distant quasars as background sources. As that ultraviolet light passes through Andromeda's halo on its way to us, certain wavelengths get absorbed by atoms and ions in the halo gas. By measuring the absorption, the project mapped the halo's extent and composition. The result was startling. Andromeda's halo extends roughly 1.3 million light-years from the galaxy's center, roughly half the distance between Andromeda and the Milky Way, and our galaxy has a similar halo extending in all directions for a comparable distance. When you do the arithmetic, the two halos do not just nearly meet, they overlap. There is no empty space between Andromeda and the Milky Way anymore. The two galaxies share a tenuous outer atmosphere. The atoms of our halo are mingled at the boundary with the atoms of theirs. In some literal physical sense, the merger has already begun, only at the diffuse outer envelope level. The cores of the two galaxies, where the stars and the bulk of the mass live, are still 2.5 million light-years apart, but the halos overlap. Andromeda is, in that diffuse sense, already here. Let that sit for a moment. The atoms of Andromeda's outer atmosphere are, right now, mingled with the atoms of ours. The galaxy you can see as a faint smudge in the autumn sky is not a distant island. It is the bright core of an envelope that extends outward to where ours extends inward. We are inside Andromeda's outer envelope right now, and Andromeda is inside ours. Now, before this picture becomes too vivid, it is worth understanding what the halo actually is. The halo gas is extraordinarily diffuse. It is mostly hydrogen and helium, with trace amounts of heavier elements. It is hot, typically hundreds of thousands of degrees, though some components are much cooler and some much hotter, and it is ionized, meaning the atoms have been stripped of their electrons. The density is so low that, in any practical sense, it is closer to a hard vacuum than to anything we would call an atmosphere on Earth. There are perhaps a few atoms per cubic centimetre in the densest parts. Most of the halo has fewer atoms per cubic metre than the best laboratory vacuum on Earth. So when I say that Andromeda is already touching us, I mean it in a precise but limited sense. The halo gas does not slow down spacecraft. It does not register against any background you would normally measure. It is not a medium you could swim through, but it is there. Atoms of it are present right above the Milky Way's disk and outside the solar system, mingled with atoms of the Milky Way's own halo. The two galaxies have been, in this very diffuse sense, in physical contact for billions of years. Sharpen the paradox of the title. The destination is touching us. Pieces of it are interleaved with pieces of us in the gas above and around the local group. And the destination is still unreachable. The two galactic cores remain 2.5 million light-years apart, in spite of the halo contact, and the cores are what we mean when we talk about Andromeda and the Milky Way as separate places. This is a useful sharpening of the central thread because it strips away the intuition that distance is the only barrier. If distance were everything, then halo contact would mean partial reachability. But halo contact does not move the cores any closer in any meaningful sense. The cores of the two galaxies are still separated by a gap that defeats every form of travel we can describe. There is a quiet philosophical detail worth dwelling on. The halo discovery, when it was made public in 2020, was a small piece of news that did not get the attention it probably deserved. It is one of those discoveries that quietly redraws the map of what we mean by the universe. For most of human history, we have thought of stars and galaxies as bright points scattered across an otherwise empty cosmos. The halo work and similar work on the Milky Way's own halo and on the halos of other galaxies has revealed that the universe is much more continuous than that. Galaxies are not isolated islands in empty space. They are dense cores surrounded by enormous diffuse envelopes, and those envelopes interpenetrate. Within the local group, the picture is even more remarkable. The local group consists of about 50 known galaxies, the largest of which are the Milky Way and Andromeda. Many of the smaller satellite galaxies, the Magellanic Clouds, M32, M110, dozens of dwarf galaxies orbit one or the other of the two large galaxies, embedded in their respective halos. The local group is, in this view, not a constellation of separate islands, but a single connected structure, gravitationally bound, with diffuse gas extending throughout and dense cores at the largest gravitational anchors. This connects to the central thread in a particular way. Andromeda is not a distant island we need to get to. It is the bright core of an enormous structure that we are already part of. In some senses, the question, how do we reach Andromeda, is the wrong question. We are already in contact with its outer parts. The real question is, how do we get to the core? And the core is what every wall in this video makes impossible. The contact at the edges does not transfer to the cores. Add some detail about the halo's composition. The gas is mostly hydrogen, mostly ionized, hot enough to glow weakly in ultraviolet. Heavier elements, oxygen, carbon, nitrogen, magnesium, silicon, are present in trace amounts. Some of these heavier elements are the products of stars that lived and died inside Andromeda's disk over the past several billion years, then ejected their outer layers as planetary nebulae or supernova remnants, then drifted outward into the halo over hundreds of millions of years. The halo, in other words, is partly a record of Andromeda's stellar history, written in the diffuse atoms ejected by long-dead stars. When you look at the night sky and find Andromeda's faint smudge, you are seeing only the brightest, densest core. The rest of Andromeda, its outer disk, its globular clusters, its dwarf satellites, its diffuse halo, extends far beyond what you can see. The visible smudge is only part of the iceberg. The full extent of Andromeda overlaps with the full extent of the Milky Way, and we are inside it. There is one more strange consequence of all this. If the halos already touch, then in some sense, the merger is not a future event. It is a process already underway. The cores will move closer to one another over the next 4 to 6 billion years. Stellar populations will increasingly interpenetrate. Gas clouds will collide more intensely. Star formation will burst. The eventual settled Milkomeda elliptical will form over many billions of years, but the diffuse contact between the two galaxies has already started. There is no clean before and after picture. Connect back to the central thread. The picture of unreachability is not two distant islands separated by empty space. It is two cores embedded in overlapping envelopes, with the cores still beyond any conceivable travel scheme. The contact at the edges does not bring the destinations any closer in any meaningful sense. The cores remain unreachable. The halos already touch. And there is the next twist, the one we are about to walk into. If Andromeda's outer envelope already touches us, what does it mean to say Andromeda now? What time is it in Andromeda right now? The question sounds simple. The answer is one of the strangest in physics. Andromeda does not have a single now. It has many. And which one you call now depends on how you are moving. The next part walks into the relativity of simultaneity and into one of the most unsettling thought experiments ever proposed in modern physics the Andromeda paradox. Is less than break time equals 1s is greater than number. Part 8. The relativity of now. We have been talking about Andromeda as a single fixed place, very far away, that we are trying to reach. But Einstein's theory of special relativity tells us something that breaks even this part of the picture. At cosmic distances, there is no shared now. Andromeda does not have a single present moment. Different observers, even observers standing next to each other on Earth, disagree about what is happening in Andromeda right now, and the disagreement is not philosophy. It is a measurable, calculable consequence of the geometry of spacetime. The thought experiment that makes this most vivid was popularized by the philosopher Hilary Putnam in the 1960s, and later refined by the mathematical physicist Roger Penrose, who used a version of it in his book The Emperor's New Mind. It is often called the Andromeda paradox, or the Putnam-Penrose paradox, or sometimes just the Andromeda thought experiment. Imagine two people standing next to each other on a street in any city. One is walking, slowly, perhaps at a casual pace of about 4 kilometers per hour. The other is standing still. They are right next to each other, perhaps even touching shoulders. They both look up at the sky, at Andromeda. Special relativity tells us that observers in different states of motion disagree about what events are simultaneous at a distance. The faster the relative motion, the larger the disagreement at a fixed distance. The further the distance, the larger the disagreement at a fixed relative velocity. For two observers in nearly the same place, moving at very different velocities, the disagreement at a great distance can become substantial. For our two pedestrians on Earth, the relative motion is small. 4 kilometers per hour is a slow walking pace, almost imperceptible against the speed of light. But Andromeda is 2.5 million light-years away. And when you multiply a small relative motion by a large distance, the result is not small. The disagreement between the walkers now in Andromeda and the standers now in Andromeda comes out to several days. Let me say that more slowly. Two people standing next to each other on Earth, one walking and one standing still, disagree about what is happening in Andromeda right now by an amount equal to several days. If something is occurring this moment in Andromeda from the walker's perspective, it might already be in the past, from the stander's perspective, or still in the future. Both perspectives are equally valid. Both are physically correct. There is no privilege now that determines which one is the real present moment in Andromeda. There are only the perspectives of the two observers. This is not metaphor. This is not philosophy. This is special relativity, the same theory that GPS satellites use every second, the same theory that has been confirmed in every imaginable experiment over the last 100 years. It is the geometry of space-time applied to objects that are far apart. Penrose's original use of this thought experiment was to push the point even further. He imagined that something specific was happening in Andromeda, say, a fleet of starships preparing to launch toward Earth, or a decision being made by a government, or some other identifiable event. From the walker's perspective, the event has already happened. From the stander's perspective, it has not yet happened. Both views are simultaneously correct. There is no fact of the matter, in the universe's view, about whether the fleet has launched or not. This has been used by philosophers as an argument for what is called block universe or eternalism, the view that the past, present and future all exist with equal reality, and that our experience of now as a moving moment is an illusion of our specific perspective rather than a property of the universe itself. Whether or not you find that interpretation compelling, the underlying physics is solid. The disagreement between observers about distant simultaneity is a real, measurable feature of how space-time works. Now connect this back to the central thread. We have been talking about Andromeda as a destination, a place you could in principle try to reach. But the relativity of simultaneity reveals that Andromeda does not have a single fixed time. There is no single present moment in Andromeda that all observers share. There are only the family of simultaneity slices, one per observer, all of them equally valid, none of them privileged. This is, in a strange way, another wall between us and Andromeda. The destination is not a single point in space at a single moment in time. The destination is a region of space at a fuzzy region of time, where time is observer-dependent and there is no shared answer. The intuition of going there presumes a destination that exists at a definite moment. The geometry of space-time denies that intuition. Add the deeper, unsettling fact. The same is true between any two distant points in the universe. Strictly, there is no universal now anywhere. Even within the solar system, the disagreements between observers about distant simultaneity exist. They are just unmeasurably small at the velocities and distances involved. At the Sun's distance, the disagreement is tiny. At Pluto's distance, slightly larger. At the nearest star, a few hours. At Andromeda, several days. At the further reaches of the visible universe, thousands or millions or billions of years. The deeper into the cosmos you look, the wider the disagreement about now becomes. There is no shared cosmic present. Everything is relative to the observer, and the disagreement grows with distance. This has a strange consequence for the very idea of interstellar travel. A traveller moving from Earth to Andromeda at near light speed has a clock that runs differently from Earth's. They also disagree, by enormous amounts, about what is happening at Andromeda during the trip. The now, they call current, in Andromeda at any moment of the journey, is a different now than someone on Earth would call current. They are not heading to a fixed point in time. They are heading to one of an infinite family of Andromedas, and the one they actually arrive at depends on every detail of their motion along the way. There is something deeply strange about this. Most of us, when we picture a journey, picture a destination that exists at a definite moment in the future. The traveller will arrive at this place at that time. The relativity of simultaneity says that, for any cosmic destination, that time is not well defined. It depends on the traveller. It depends on every other observer. It is observer relative all the way down. For a destination as far away as Andromeda, the observer relativity is not a small correction. It is a major feature of the destination. The Andromeda you arrive at, in your reference frame, is genuinely different from the Andromeda someone else would arrive at in a different reference frame, not because the place is different. Because the geometry of space-time does not permit a single shared answer to the question, what is happening in Andromeda right now, there is one more wrinkle worth pointing out. The relativity of simultaneity argument does not require any travel at all. It applies just to perception. Two observers on Earth, right now, disagree about what is currently happening in Andromeda. Right now, while you sit reading this script or listening to this narration, your now in Andromeda is different from the now of someone driving past you in a car. The disagreement is built into the structure of space-time. This is, to my mind, one of the strangest properties of the universe. Not because of what it implies for travel that's just a downstream consequence, but because of what it implies about reality itself. The universe does not have a shared present. There is no privileged moment that defines what is happening everywhere at once. There are only frames of reference, each with their own now, all equally valid. Call back to the central thread. Connect this back to the central thread by noting that even if every previous wall distance, energy, biology, the speed of light were somehow broken, the destination would still not exist as a single fixed place. Andromeda is unreachable, not just because the trip is impossible, but because the place you are trying to reach is, in a meaningful, relativistic sense, not one place at all. The geometry of spacetime denies the destination, the kind of singular existence that the idea of going there requires. Andromeda is a smeared region of an unrecoverable past, a present that depends on the observer, and a future that no human can ever reach. There is no there to go to. There are only many possible theirs, and the wall reaches across all of them. And there is yet another layer to walk into. Even setting aside the relativity of simultaneity, there is something else strange about how we see Andromeda. We do not see what is there, we see what was there. Every photon arriving from Andromeda is an image of the galaxy as it existed 2.5 million years ago. The Andromeda we see in our telescopes, in our naked eye sky, in any image ever taken, is the Andromeda of the distant past. We have never seen the current one. We will never see the current one. And by the time anyone could possibly arrive there, the destination will have aged twice over again. The next part walks through what it means to chase a fossil. Is less than break time equals 1s is greater than number. Part 9. Looking at the past, always. Hold in mind the picture from the previous part. The destination's now is observer dependent. There is no single present moment in Andromeda. Now add a separate strange property, one that compounds with the relativity of simultaneity rather than cancelling it. We have never seen the current Andromeda. We have never seen any Andromeda except the one as it existed 2.5 million years ago. Walk slowly into this. Light takes time to travel. The light from your computer screen takes a few nanoseconds to reach your eye. The light from the room around you takes a similar fraction of a second. The light from the moon, when it is shining at night, takes about 1.25 seconds to cross the gap. The light from the sun takes about 8 minutes. The light from the nearest star Proxima Centauri, 4.24 light-years away, takes 4 years and 3 months. Every photon you have ever seen represents an image of its source at some moment in the past, not in the present. Apply this to Andromeda. Every photon arriving at your eye tonight from the Andromeda galaxy left the galaxy about 2.5 million years ago. It has been travelling at 300,000 kilometers every second the entire time just to get to your retina. That photon is older than the human species. The Andromeda whose image you see was the Andromeda of 2.5 million years ago. What was happening on Earth 2.5 million years ago when that light departed? Let's walk through the answer in slow detail, because the comparison is what makes the duration vivid. 2.5 million years ago on Earth, modern humans did not exist. The genus Homo had just begun to appear. The most advanced human-related species was probably Homo habilis, sometimes called handyman, for the simple stone tools associated with their fossils. Their brains were about half the size of ours. They lived in small bands in eastern Africa, walking the savannas around what is now Tanzania and Kenya. Their toolkit consisted of simple chipped stones. They did not have fire under their reliable control. They did not have language as we would recognize it. They did not have permanent dwellings. They did not have agriculture. And the light leaving Andromeda at that moment, light from stars that had been burning for billions of years, light from the same diffuse halo we have been talking about, light from spiral arm structures and clusters of forming stars, and the central bulge, that light started its journey then and has been travelling ever since. During those 2.5 million years of light travel, the entire arc of the human story unfolded. Homo habilis was replaced by Homo erectus, which spread out of Africa and across the continents. Homo erectus was replaced by Homo sapiens, by Neanderthals, by Denisovans, and by other, less well-known forms. Eventually the other forms went extinct, and only Homo sapiens remained. Our species developed language, controlled fire, invented increasingly complex tools, painted on cave walls, built shelters, domesticated animals, cultivated plants, invented writing, founded cities, built empires, smelted metals, harnessed steam, generated electricity, split the atom, launched satellites, and put telescopes in space to study the very photon that finally arrived to be detected. Every word of that history happened while the photon was in transit. The photon you see tonight is older than every story your species has ever told. Sharpen the strange consequence. The Andromeda you see in any image, by naked eye, by telescope, by JWST, by any instrument, is not the Andromeda that exists right now. It is the Andromeda of 2.5 million years ago. The current Andromeda, the one that exists at this moment in the universe's evolution, is invisible to us. We will not see what Andromeda looks like today for another 2.5 million years. Walk through what this means concretely. Stars in Andromeda that you can see in any image have, in many cases, already changed during the intervening 2.5 million years. Some of them have exhausted their fuel and exploded as supernovae. Some have evolved off the main sequence into giants and shed their outer envelopes. Some have changed brightness dramatically. The current configuration of stars in Andromeda is not the configuration we see. It is somewhere else entirely. This is not unique to Andromeda. Every object in the night sky shows us light from some past moment. The Sun is 8 minutes old. Proxima Centauri is 4 years old. The center of the Milky Way is 26,000 years old. Andromeda is 2.5 million years old. The most distant galaxies the James Webb Space Telescope can see are 13 billion years old. The night sky, properly understood, is not a snapshot. It is a layered fossil record, with the most distant galaxies showing us the earliest moments of cosmic history. The current universe, as it exists right now, is something we have never seen and will never see in full. We see only the past. What this means for the central thread is unsettling. Even if you could somehow break every other wall, even if you could traverse the distance, fund the energy, survive the biology, sidestep the time dilation, and overcome the relativity of simultaneity, you still could not arrive at the Andromeda your telescopes show. The Andromeda your telescopes show is the past. The Andromeda you would arrive at is, at minimum, 2.5 million years further along in its evolution, because that is the absolute minimum time the journey takes for any signal. In practice, for any conceivable mission, the arrival is in an even more distant future of Andromeda, at least 4 or 5 million years past the version we see in current images. The destination, in its current state, has never been observed. It will never be observed, and no human or descendant of humans will ever stand in it. Add a soft horror to this. The faint smudge in the autumn sky might already be different now from how it appears. We cannot know. The galaxy, as it actually exists, 2.5 million years past the image we see, may have already shifted into a configuration we will not learn about for another 2.5 million years. Even our most modern measurements, JWST imagery, Hubble surveys, Gaia parallaxes, all show us light that is 2.5 million years old. None of them show the current galaxy. The traveller going to Andromeda is, in effect, chasing a photo album rather than visiting a place. The album shows where the place was. The place itself has moved on. There is a quiet philosophical point hiding here. We have built our sense of the universe out of light. Everything we know about anything in the cosmos comes through the photon. Every measurement, every image, every survey, and the photon is always old. Sometimes only nanoseconds old when you're looking at your hand. Sometimes 13 billion years old when you're looking at the most distant galaxy, but always old. We are, in a sense, never really in contact with the present universe. We are always in contact with the universe as it was. The present universe, whatever that even means, given the relativity of simultaneity, exists only as a kind of theoretical extrapolation from the layered fossil record of light that has actually reached us. The actual current state of any distant object is, in principle, inferable, but never directly observable. For Andromeda specifically, this is intense. The galaxy is bright enough and large enough that we have detailed images of its past self. We can study its star formation history, its dust distribution, its halo composition, its motion against the cosmic background. We know an enormous amount about the Andromeda of 2.5 million years ago. We know nothing about the Andromeda of now. The current Andromeda is a sealed envelope that will only open, slowly, 2.5 million years from this moment forward, as future telescopes pick up the photons that are leaving Andromeda right now. Connect back to the central thread. Andromeda's unreachability is not just a problem of getting there. It is a problem of even knowing what there looks like right now. We see what it was. We cannot see what it is. And we cannot reach what it will be by the time anyone could arrive. The destination exists in a layered set of states, past visible, present invisible, future inaccessible, and the wall between us and any of those states is impassable. We have walked through many walls now: distance, energy, the speed of light, time dilation, biology, the halos already touching, the relativity of simultaneity, the antiquity of the light. Each of them, in its own way, makes Andromeda unreachable. Each of them, alone, would be enough. Stacked together, they build a fortress around the destination that no possible imagination can breach. But there is one more layer to walk through: the merger. We have touched on it a few times. The fact that Andromeda is approaching, that the two galaxies will collide in roughly 4.5 billion years, that the merger will settle out into Milkomeda over roughly 6 billion years total. We have noted that this approach does not make the trip easier, because the Earth and the Sun cannot wait that long. But the merger deserves its own slow walkthrough, because the math of the Sun's lifetime is itself a barrier as strict as any other on the list. The destination is coming. We will not be here. Let's see why. Is less than break time equals 1s. Is greater than number part 10. The merger nobody will be alive to see. The merger, in its modern form, has been modelled extensively. The numbers vary slightly depending on which paper you read and which dataset is used, but the broad picture is consistent. In about 4.5 billion years from now, the central regions of Andromeda will sweep through the outer regions of the Milky Way for the first time. The first encounter is a glancing pass rather than a head-on collision. The two galaxies move through one another from oblique angles, like two flocks of birds whose paths cross. During this first pass, the gravitational fields of each galaxy distort the other. Stars from each system are pulled into long tidal streams, stretching for hundreds of thousands of light years. The disks of both galaxies warp dramatically. Gas clouds, which are much more diffuse and continuous than the stars, collide with one another and compress, triggering enormous waves of new star formation across both systems. The combined galactic structure looks chaotic, with arms of stars flung out in unexpected directions, with bright bursts of newborn star clusters glowing in the regions where the gas has compressed, with dust lanes redistributed and rearranged. After the first pass, the two galaxies separate again, pulled apart by their own remaining momentum, but bound now by their mutual gravity. They recede from each other for a while, then return. The second pass occurs roughly 1 billion years after the first. The dance continues, with each pass progressively tightening the orbital embrace. The cores of the two galaxies, the dense central bulges, where the supermassive black holes live, spiral inward toward each other. By roughly 6 billion years from now, the cores merge. The combined galaxy settles into a single elliptical structure, much larger than either of the original spirals, but without the same elegant disk shape. The spiral arms of both galaxies have been disrupted beyond recognition. The new galaxy, called Milkomeda or Milkdromeda in popular astronomy, is a relatively featureless elliptical with smooth distributions of stars and a more spherical overall shape. The two supermassive black holes, Sagittarius A star at the Milky Way's center, with a mass of about 4.15 million solar masses, and M31 star at Andromeda's center, with a mass of roughly 100 to 230 million solar masses themselves, spiral together over millions of years and eventually merge. The merger releases a burst of gravitational waves that, while extremely difficult to detect from our perspective today, would shake spacetime across the cosmos and be detectable by sufficiently sensitive instruments anywhere in the visible universe. The picture is clean. The destination, in roughly 6 billion years, becomes the same place as our own galaxy. Andromeda and the Milky Way become Milkomeda. No need to travel anywhere, the destination has, in a sense, travelled to us. So why is this not the answer to the question, is Andromeda reachable? Because the math of the Sun's lifetime and the math of Earth's habitability foreclose any human presence at the time of the merger. Let me walk slowly through that math, because it is genuinely sobering. The Sun is about 4.6 billion years old, give or take a few tens of millions. It is currently in its main sequence phase, the long, stable, hydrogen-burning phase of its life. The main sequence will last for about another 5 billion years. After that, the Sun will swell into a red giant, expand past Earth's current orbit, and eventually shed its outer layers into space, while its core collapses into a white dwarf. The whole transformation, from late main sequence through red giant through white dwarf, will play out over about 1 billion years. So at the 4.5 billion year mark, when Andromeda is making its first close pass through the Milky Way, the Sun is in its very late main sequence phase, just before the expansion. It is still burning hydrogen, but only barely. Its luminosity has been gradually increasing for billions of years, and by that point it is significantly brighter than it is today. Now, what is Earth doing at the 4.5 billion year mark? Earth, in any classical sense, ended its habitability phase long before. The slow increase of solar luminosity over the past 4.6 billion years has gradually warmed the planet. The trend continues into the future. About 1 billion years from now, the Sun will be bright enough to drive Earth's surface temperature past the threshold at which water can remain liquid on the surface. The oceans will evaporate into the atmosphere. Water vapor is itself a greenhouse gas, so the warming accelerates. The surface temperature rises rapidly. Eventually, the planet becomes Venus-like, a hot, dry, atmospheric oven with no liquid water and no life as we know it. Let me restate that. About 1 billion years from now, Earth becomes uninhabitable due to solar luminosity increase. That's 1 billion years from now. The merger with Andromeda starts at 4.5 billion years. There is a 3.5 billion year gap between Earth becoming uninhabitable and the merger beginning. Earth's habitability ends long before Andromeda gets here. If humans somehow continue to exist after Earth's habitability ends, perhaps by migrating outward in the solar system, perhaps by living in artificial habitats, then their continued existence depends on whatever they can engineer to substitute for Earth. Mars becomes more habitable as the Sun warms, though by the time the warming makes Mars Earth-like, Earth has already passed Mars-like and become Venus-like. The window for a habitable Earth and a habitable Mars never opens simultaneously. Past the 1 billion year mark, the inner solar system becomes progressively more hostile. By about 5 billion years from now, the Sun begins its red giant expansion. The outer envelope of the Sun swells past Mercury's orbit, then past Venus, then approaches Earth's. Whatever is left of Earth at that point, likely a dry, dead, rocky ball, is either absorbed by the Sun's expanding envelope or pushed slowly outward by the Sun's mass loss as it sheds its outer layers. So even if humans somehow last billions of years past Earth's habitability ending, the solar system itself becomes inhospitable long before the merger completes. The inner planets are absorbed or destroyed. The outer planets and their moons may briefly become more habitable as the Sun's expanded envelope warms them, but only briefly. By the time the Sun finishes its red giant phase and collapses into a white dwarf, around 6 billion years from now, the entire solar system is essentially dead. That is, roughly, when the merger with Andromeda completes. The Sun, by that point, is a small, dense, slowly cooling white dwarf about the size of Earth, with the mass of the Sun glowing faintly from residual heat. Anything orbiting it is either gone or frozen. There is no warm world. There is no place to stand and watch the merger. Connect to the central thread directly. The destination is coming. The destination is unreachable. The Sun is dying on a faster clock than the merger is closing. There is no future in which a human, descended from us, lives on a planet around the Sun and watches Andromeda's stars become close enough to map. The Earth we live on cannot wait that long. The Sun we orbit cannot wait that long. The species we are cannot wait that long. This is one of the quietly devastating facts in this video. The destination would arrive, in some sense, if we just waited, and the waiting cannot be done. The home where we wait, the Sun whose light we live by, the planet whose surface we walk on, all expire on a timescale faster than the destination's approach. There is a softer version of the same point. Even if humanity does survive by migrating outward, by engineering artificial habitats, by evolving into something biologically very different from ourselves by the time the merger completes, the descendants will be so changed that it is questionable whether they are still us in any meaningful sense. A species that has lived through 6 billion years of cosmic and evolutionary upheaval is not the species we are. It might be related, it might trace its lineage back to us, but it is not us. So even the romantic version of the merger, in 6 billion years, our descendants will watch Andromeda fuse with the Milky Way, has to be qualified. Whatever exists then, if anything, is something other than us, on the far side of every connection to the present civilization. Add the M33 wrinkle. The Triangulum galaxy may already have had a close encounter with Andromeda within the last few billion years, leaving tidal signatures in both. The future merger may include M33 as a participant, and Andromeda may merge with it first. The three-galaxy interaction is being modelled and remodeled as new data comes in from Gaia and JWST. Add the 2024 debate. Updated Gaia data, analysed in 2024, suggested the probability of a definitive merger with the Milky Way within the next 10 billion years may be closer to 50% than to certainty. The galaxies may glance off each other repeatedly without binding. The merger picture, long popularized as inevitable, may be only one possible outcome. Even the destination's arrival may not happen. If the merger does not happen as predicted, then the destination remains where it has always been, far away, approaching slowly, but not approaching all the way, in which case Andromeda is even more permanently unreachable. The wall, in that scenario, never thins. The cores stay distant, the gap stays open, the Sun dies before anything bridges it. Either way, the wall holds. The destination either comes to a solar system that has already ended, or fails to come at all. Both outcomes leave humans on the wrong side. This is a quiet point worth resting on. The merger has been popularized as a comforting cosmic union, the friendly approach of a sister galaxy, the eventual blending of two stellar communities into a single new home. It is none of those things. It is a process that unfolds over timescales that comfortably exceed the survival horizons of everything we are and care about. The cosmos is patient, we are not. End on the open loop. We have looked at the merger. We have looked at the lifetime of the Sunday. We have looked at the timescales involved and seen how badly they outpace any human survival window. Now look outward, beyond the local group, and consider what the rest of the universe is doing. Because the rest of the universe, every galaxy beyond the local group, every cluster, every supercluster, every cosmic structure is moving in a direction that makes even Andromeda's unreachability look mild. Most of the universe is running away from us, and most of it is running faster than light can chase. The next part walks through the cosmological event horizon and what it means for the larger picture of reachability. Is less than break time equals 1s is greater than. Number. Part 11. The receding horizon and the cosmological event horizon. Step back from Andromeda for a moment. We have spent the script demonstrating that the closest major galaxy in the universe is permanently out of human reach. Now zoom out and consider everything else. The universe contains, by best estimates, between 100 billion and 2 trillion galaxies, depending on how you count. Andromeda is the nearest peer. The rest are further away. Most are much further away, and most are doing something that makes them even more permanently unreachable than Andromeda. Most of them are receding from us, and most of them are receding faster than the speed of light. Let me walk slowly into that last sentence, because it sounds like it violates special relativity, and it does not. The recession of distant galaxies is not motion through space. It is the expansion of space itself. The distance between us and every distant galaxy is growing not because the galaxies are moving through space toward greater separation, but because the space between us is stretching. The stretching is not constrained by the speed of light limit, which applies to motion through space. Space itself can expand at whatever rate the geometry of the universe dictates. The discovery that the universe is expanding came from Edwin Hubble in 1929, the same astronomer who had measured Andromeda's distance a few years earlier. By looking at the redshifts of light from many distant galaxies, Hubble noticed a pattern. The further away a galaxy was, the faster its light was redshifted. The relationship was linear. He inferred that all galaxies were receding from us, and that the recession velocity scaled with distance. The interpretation that emerged was that the universe itself was expanding. The expansion has been refined and confirmed many times since. The current best estimate of the Hubble constant, the rate of expansion, is around 70 kilometers per second per megaparsec. That means a galaxy 1 megaparsec away, about 3.26 million light-years, is receding from us at 70 kilometers per second due to the expansion of space alone. A galaxy at 2 megaparsecs is receding at 140 kilometers per second, and so on. The further away a galaxy is, the faster the space between us is stretching. Eventually, at large enough distances, the rate of recession due to expansion exceeds the speed of light. The galaxies at those distances are moving away from us faster than light can travel between us. Their photons emitted today, even moving at the maximum speed the universe permits, can never reach us because the space between us is expanding faster than they can cross it. This defines what is called the cosmological event horizon. It is the distance beyond which any light emitted toward us today will never arrive. Galaxies beyond the cosmological event horizon are causally disconnected from us. We cannot reach them. We cannot send signals to them. We cannot receive any new signal from them after a certain point. They are not just hard to reach. They are absolutely sealed off by the structure of cosmic expansion itself. The current cosmological event horizon sits at roughly 16 billion light-years. Galaxies inside that distance can still, in principle, exchange light with us in the future. Galaxies beyond it cannot. Every year, the cosmological event horizon shrinks slightly relative to the moving distance to distant galaxies because the expansion is accelerating. Every year, more galaxies slip beyond it. The universe is becoming progressively more isolated on the largest scales as more of it crosses the event horizon outward. Now, connect this back to Andromeda and the central thread. Andromeda is gravitationally bound to the Milky Way. The local group Andromeda, the Milky Way, M33, and the dozens of dwarf satellites is a small region of the universe where gravity wins over expansion. Within the local group, the galaxies do not recede from one another due to cosmic expansion. They are too close, too tightly bound by mutual gravity. The expansion is happening, but its effect within the local group is overwhelmed by the gravitational pull. So Andromeda is one of the very few major galaxies in the universe that is not receding from us. It is, in fact, approaching us, as we have discussed. It is also one of the very few galaxies that will not slip beyond the cosmological event horizon. It is locked in with us by gravity. Even as expansion accelerates, and more of the universe slides away beyond the horizon of reachability, Andromeda will remain a member of the local group, bound to whatever the Milky Way becomes, for as long as the universe permits. This is, in a strange way, what makes Andromeda's unreachability so deeply telling. Andromeda is the time's best case. Andromeda is the closest, the most stable, the most gravitationally bound, the easiest possible interstellar destination outside our own galaxy. And it is still impossible. What does that say about everything else? Apply the cascade we have built to any galaxy beyond Andromeda. Distance, greater. Energy required to reach it, greater. Travel time at any given speed, longer. Time dilation effect required to compress the subjective experience, more extreme, with more compounded loss of any home civilization. Biology, more strain on any sealed system. Light delay, more antique by the time it arrives. Relativity of simultaneity, larger disagreement between observers about distant now. And on top of all that, the destination is receding due to cosmic expansion, making the closing distance worse rather than better. For galaxies more than a few 100 million light-years away, the recession from cosmic expansion becomes significant. The light traveling from them to us is stretched substantially. The space between us is growing measurably. And for galaxies near or beyond the cosmological event horizon, the situation becomes absolute. Even at the speed of light, you cannot reach them. The expansion outpaces any possible travel. So Andromeda is not the worst case. Andromeda is the best case for any major galaxy beyond our own, and it is still permanently out of reach. The implication is that nearly every other galaxy in the universe is permanently out of reach, and is so by an even larger margin than Andromeda is. There is one more refinement worth mentioning. The Dark Energy Spectroscopic Instrument DESI released results in 2024 that hinted at something subtle but potentially important. The data suggested that dark energy, the mysterious force driving cosmic expansion, may not be a true constant. It may have been slightly stronger in the distant past, and may be weakening over cosmic time. If this finding holds up under further analysis, and it remains an active area of research, with the picture still being refined, then the future trajectory of cosmic expansion may be slightly different from what we have long assumed. The change would not be enough to alter the central picture of Andromeda's local approach, which is dominated by gravity at small distances. But it might change the timing of when distant galaxies cross the cosmological event horizon. The receding horizon might shrink more slowly than previously expected, or might eventually stabilize at a fixed moving distance, or might do something else more complex. This is a piece of live science, not settled fact. The DESI hints are tantalizing, but not conclusive. Whether dark energy is exactly constant, slowly weakening, or doing something else more complex remains to be definitively established. What is certain is that, on the timescales relevant to interstellar travel, millions to billions of years, cosmic expansion will continue to push most galaxies further away from us, and most galaxies are already moving outside the horizon of reachability. Cull back to the central thread. Connect this back to the central thread by noting that the cosmic scale geometry of expansion is the largest of the walls between us and the universe. Andromeda may be the only major galaxy that is even theoretically still on the right side of the cosmological event horizon, gravitationally bound to us, and even it is foreclosed by every other wall in the cascade. Every other destination beyond the local group is foreclosed twice over, once by the same cascade that makes Andromeda unreachable, and once more by cosmic expansion that makes it actively retreat from us. If Andromeda is impossible, the rest of the universe is more than impossible. The most distant galaxies are not just unreachable, they are slipping permanently beyond the horizon of even theoretical contact. The picture is, in its full extent, deeply isolating. Almost everything we can see is moving away from us. Almost all of it is becoming progressively less reachable over time. The few exceptions, the local group, are bound to us by gravity, but the cascade of walls makes them no easier to actually visit. We are, in every direction we look, increasingly alone, and in the longest cosmic future, the isolation becomes complete. Even the local group will eventually be the only thing we can see. Every other galaxy, every other cluster, every other piece of cosmic structure will slip beyond the cosmological event horizon. The night sky for any future observer in the merged remnant of the Milky Way and Andromeda will contain exactly one galaxy, their own. The rest of the visible universe will be invisible permanently. The next and final part walks through that strange, lonely future and lands the deepest implication of the entire video. The closest place we can never reach is also what humanity eventually becomes. Is less than break time equals 1s is greater than number part 12. The last galaxy in the sky. Look ahead, far ahead. Project the universe forward by about 100 billion years from the present moment. The current age of the universe is roughly 13.8 billion years, so 100 billion years from now is more than 7 times the universe's current age. We are looking far past anything most people normally think about. We are looking into the far future. By that point, cosmic expansion will have pushed every galaxy outside the local group beyond the cosmological event horizon. Every cluster, every supercluster, every cosmic filament, every void, all of it will have slipped beyond the horizon of causal contact with us. Their light will no longer be able to reach the location where the local group sits. They will be invisible. They will be undetectable by any means we know how to describe. They will be, in every functional sense, no longer part of the universe that any observer in the local group can experience or measure. The local group itself will have settled into a single merged system. The Milky Way and Andromeda will have completed their merger many tens of billions of years earlier. The Triangulum galaxy will have joined the combined system. The Magellanic Clouds, which are currently spiraling slowly inward toward the Milky Way, will have been absorbed long before. The dozens of smaller dwarf galaxies Sagittarius, Sculptor, Draco, Ursa Minor, Fornax, the rest will all have been gradually pulled in and tidally disrupted, their stars scattered into the merged elliptical structure. What remains is one galaxy, Andromeda, an enormous elliptical with smooth distributions of stars, no spiral arms, no clear distinction between what was once the Milky Way and what was once Andromeda. The two supermassive black holes will have merged into a single, more massive black hole at the center, a remnant of the gravitational dance billions of years earlier. Star formation will have slowed dramatically as the gas reservoirs of both progenitor galaxies have been used up, ejected, or run too thin to spawn new stars. The galaxy will be reddish, dominated by old, long-lived, low-mass stars. The sharp blue spiral arms that once decorated both progenitor galaxies will be a distant memory in the geological history of the merged remnant. Future astronomers on a planet orbiting some descendant star within Andromeda, if any such astronomers exist, 100 billion years from now, will look up into a night sky that contains exactly one galaxy, their own. The sky will be dark beyond Andromeda. The cosmic microwave background, the faint glow from the Big Bang itself, will have stretched into wavelengths so long that conventional instruments may not even detect it. The dark sky will be uniform, featureless, without anything to indicate that any other galaxy or any other large-scale structure ever existed. Walk slowly through what this means. Modern cosmology was made possible by observing distant galaxies, measuring how they recede, how their light has stretched, how their distribution maps the early universe, how the cosmic microwave background reflects the moment of recombination. All of that evidence is observational. All of it requires being able to see distant galaxies and distant remnants of the early universe. None of it will exist for astronomers in Andromeda 100 billion years from now. They will be unable to deduce that the universe is expanding because they will see no distant galaxies receding. They will be unable to deduce that there was ever a Big Bang because the cosmic microwave background will be too faint and too redshifted to detect. They will look out at the cosmos with the most advanced telescopes their civilization can build, and they will see only their own galaxy. Their best models will assume that Andromeda is all there is. The very science of cosmology, as we know it, will be impossible for them. This is one of the strangest implications of modern cosmology. We, the people listening tonight, are living in a brief cosmic window of visibility. The window opened roughly when the universe became transparent, around 380,000 years after the Big Bang. It has been open ever since, allowing observers, in any sufficiently developed civilization, in any galaxy, to look outward and discover cosmic expansion and the early history of the universe. The window will not stay open forever. By 100 billion years from now, only Andromeda will be visible from within it. The cosmological window will have effectively closed. We are living in one of the few epochs in the universe's entire future during which its full nature is even potentially knowable. Now bring this back to the central thread. Andromeda is, in this picture, the closest of all the galaxies, the easiest of all the destinations, the most patient of all the strangers in the cosmos, and it is also unreachable permanently by every measure that matters. But Andromeda is also something else. Andromeda is what we become. The merger does not just close the gap between Andromeda and the Milky Way. It dissolves the distinction. 6 billion years from now, there is no Andromeda anymore, and there is no Milky Way anymore. There is only Andromeda. The two former galaxies have interpenetrated, redistributed, and merged into a single new structure. The destination has, in the deepest sense, become the home. This is the strangest implication of the entire video, and it deserves to be stated slowly. The closest place humanity will never visit is also the place humanity will, in the longest run, become. The unreachable destination merges with the home and erases the distinction. There is no Andromeda to reach, because Andromeda eventually becomes us. We are not a separate civilization that visits another. We are part of a process that, over billions of years, fuses the two galaxies into one, with no possibility of any visit, but with every possibility of inheritance. If any descendants of humanity exist 100 billion years from now, in some form, in some configuration, around some star in Andromeda, they will be looking out at a night sky that is the merger of what we now call Andromeda and what we now call the Milky Way. Their galaxy contains stars that were once Andromedas. They live within a structure that is partly built out of the destination their ancestors could never reach. They are, in a quiet cosmic sense, partly Andromedan themselves. This is not a romantic claim. It is a geometric one. The mass that currently constitutes Andromeda will, in the merged Milkomeda, be distributed among the stars of the new combined galaxy. The atoms that currently float in Andromeda's halo will mix with the atoms in our halo and become part of the merged galaxy's diffuse envelope. Some of those atoms may eventually be incorporated into new stars, new planets, new life. The destination's matter becomes the home's matter. This is a strange consolation, if it is a consolation at all. We will never reach Andromeda. No human ever will. No descendant of humanity ever will, in any meaningful sense, while remaining recognizably human. The destination is permanently sealed off from any present-day Earth observer. In every direction we have examined distance, energy, biology, light speed, time dilation, relativity of simultaneity, the antiquity of the light, the lifetime of the sun, the timescale of the merger, the expansion of the universe. And yet, on a long enough timescale, Andromeda becomes us anyway, not through travel, not through reaching, through the slow gravitational dance of two galaxies that will, billions of years from now, settle into one. The destination and the traveller merge into a single thing, after every traveller has long since died, after every memory of the journey is gone, after no one remembers Andromeda as a place, and no one remembers the Milky Way as separate from it. The closest place humanity will never go is also what humanity will, in the longest run, become. The unreachable destination is also the inherited home. The wall between us and Andromeda is absolute in every direction except the one that eventually, billions of years from now, dissolves it entirely through merger rather than through reaching. So, end on the picture. A single observer, somewhere in a future Milkomeda, perhaps 100 billion years from now, looks up at a dark night sky. Their own galaxy fills the view from horizon to horizon. Beyond it, the cosmos appears empty. They have no way of knowing that anywhere else ever existed. They have no way of knowing that the galaxy they live in was once two galaxies. They have no way of knowing that a faint smudge in some distant ancestor's autumn sky was once called Andromeda, and was, by every measure of the cosmos, just outside the reach of every imaginable human ambition. But the galaxy they are in is partly made of Andromeda. The stars around them include stars that were once Andromedas. The matter in their bodies, if they have bodies, contains atoms that drifted out of dying Andromeda stars long ago and were eventually swept into new generations of star formation in the merged remnant. They are, in a quiet cosmic sense, the long-distant descendants of the unreachable destination. The journey ends not with arrival, but with the slow recognition that the traveller and the destination were always part of the same impossible question. That is what unreachability looks like, in its full strangeness. Not a wall between two separate places. A single process unfolding over billions of years, where the two sides slowly merge, where the impossibility of the journey turns out to be the impossibility of any clean distinction between the start and the end. The cosmos does not let you reach Andromeda. The cosmos lets you, eventually, become it. We will not be there to see it happen. No human will. But the universe will continue without us. Andromeda will continue its slow approach. The sun will continue its slow expansion. Earth will pass through its long heat death long before either completes. And in some unimaginable future, Milkomeda will form, will settle, will live for tens of billions of years, and will eventually, as expansion isolates it, become the only thing in the visible universe to whoever lives within it then. The faint smudge in tonight's sky is the closest place no one will ever reach. It is also, in the longest sense, the place we are slowly becoming. The only way to truly understand that is to settle into the strangeness of it, to let the impossibility of the journey and the inevitability of the merger sit side by side in your mind, and to realize that the universe has a way of dissolving distinctions on timescales we will never live to see. Andromeda is the destination we will never reach. Andromeda is also, in a slow and entirely cosmic way, already part of us.